Hi, okay. I'm Ross. I'm going to start my screen share. So I've got the paper here. I don't have any slides, fancy slides set up, although I do have a notebook with some other material I've been working on that I can switch to later on. So I'm I guess a practitioner, if you will, an engineer by background. I live in Vancouver, BC, and I've spent quite a bit of time working on camera, video imaging systems outside of the machine learning context. But recently, in the past few years, I've really been digging in. And many of you are familiar with timm. It's a collection of PyTorch image models I've been working on as sort of a learning process to get up to speed on machine learning, and it's become quite popular, I guess, all across the board. Research, other practitioners for Kaggle challenges, and now lots of organizations are using it. So aside from the models in timm, I've been building a set of training scripts, augmentations, basically everything to reproduce some great ImageNet results as I went. And as I was doing that and reading new papers, a common theme kept emerging where old baselines were being used over and over again as a reference point for new model architectures or even new training techniques, new optimizers, etc. And I've always been a little bit frustrated to see that. And so Hugo and Hervé, they were using some timm components for several of their research papers. Diet, I think, being one of the more well-known ones. That's a vision transformer variant that applied heavier augmentation and regularization to the VIP models to achieve better results on just 1K ImageNet. So they've also been using, they've had several follow-on papers like ResMLP, Kayet, and some other transformer variants since then. And they reached out to me when I tweeted about, like, I should probably write a paper about this. And they're like, hey, we've been actually exploring some ResNet baselines for our own upcoming work, and we've got some progress that sounds similar to you, so let's collaborate. So then this paper came into being. We basically combined our most recent hyperparameters and started mixing and matching and trying to push things forward. And very quickly we went from, I guess, mid 79s with a ResNet 50 up into the mid 80s, which we hadn't seen in any other previous research or papers to that point. And so that's, yeah, that's basically how we got to ResNet Strikes Back. So I'll walk through it. So the intro basically stating that there's, aside from the architecture, there's the recipe ingredients and also measurement noise for each seed, each run you do, that you should take into consideration when you're comparing models or training recipes, ingredients. And it can be very challenging to actually fairly compare even with that in mind. So yeah, we focused on ResNet 50. There's many different architectures, but we wanted to use ResNet 50 since it's still one of the most common or popularly used baselines. The training ingredients that we selected from include many recent augmentation techniques, regularizations, and we went through several different optimizers. In terms of the augmentation, we pretty much threw everything at it. We used rand augment, cut mix, mix up in combination. We tried random erasing, although it didn't make the final cut. I use that quite extensively in my other recipes. And then in regularization, fairly standard stuff, but I did add stochastic depth support to the ResNet architecture, so that was an ingredient that helped a bit, although it was dialed back actually a little bit from what I would normally use for this. Basically all of the ingredients in the recipes, they interact. So if you have one particular ingredient that might seem to be amazing in one context, if you start throwing other things in there, you pretty much have to reevaluate everything in combination. You can't just say, well, yeah, I love this augmentation, it produces amazing results. If you add another one there, then they could interact in a way that you didn't predict, and you have to reevaluate. And I guess one of the more interesting things, the optimizer, most commonly for ImageNet CNN models, you'll see SGD. Sometimes I use RMS prop quite a bit too. Hugo and Hervé actually said, well, hey, we've actually done some recent experiments with LAM, and we actually got that working really well. And I was like, okay, that's interesting. And yeah, it ended up being what we went with for the final recipe here. But there's several other alternatives in the appendix if you make it to the end of the paper that use other optimizers like SGD and Atom, and also Atom P. So I guess one thing that was actually on discussion today in Twitter is checking seeds, and this was actually pretty interesting. We ran, I think, on the middle hyperparameters, so the 300 epoch ones. I believe it was 100 seeds, so you can see the distribution of the results across different seeds, and there's quite a bit of variation. And I think more papers should definitely do that. This table is the total results. There's the ResNet 50 architecture, specifically the 80.4. Should be noted that basically all of these results here were the ResNet 50 optimized recipe applied to all these other architectures. These results aren't necessarily the best for the other architectures. That was sort of point of the paper, that even spending all this time searching for good ResNet 50 results, the recipe that we wound up with didn't necessarily produce the best results on other architectures. You can see for the ResNets, it's actually pretty good. They improve against the baselines for most of the ResNets, but some of the other larger model architectures that might have had more augmentations or regularization already in their original papers, so their default hyperparameters, it actually potentially did worse than the originals. And since the paper was released, I've actually retrained ResNet 101 and 152 with more augmentation and regularization, and I think I got 82 at the 101 and 82.8, I believe, for the ResNet 152. And then also very recently, I did some experiments on ResNet 50 again, but using a lower resolution, a lower training resolution of 176 by 176. And I'm not sure if you guys are familiar, but the train test resolution discrepancy, you often get a peak performance at validation at test time when you train with rand augment if you validate at a higher resolution. So by training at 176 at 224, you actually end up, seems like approximately an optimal test resolution. And so I recently got an 80.68 on the ResNet 50, which I believe we're planning to put into the next revision of the paper. Although Hugo and Hervé, they have some similar experiments. I think we're going to see who ends up with the highest bump there, but I think it'll end up around 80.7. Although it should be pointed out that in terms of transfer learning and also results on some of the out of distribution alternate ImageNet test sets, it appears that training at the higher resolution is beneficial. So it may still be better to use the 224 80.4 weights if you want to use it in downstream tasks that are better at higher resolutions. So there was some transfers and ablation. So yeah, alternate training recipes. You can see some other ones here. B and C, if you follow the timm model libraries, the models there, a lot of recent, I'd say in the last year or so, weights that I've trained myself have been variations of B and the C.1. Recently, C.2 I've been using a bit more. And then D was an experiment run, I guess, motivated by the LAM optimizer performance. Wanted to see if there was other optimizers that we could get to a similar level for like trying to pass 80, although it didn't achieve it on this run, but or on this set of experiments. But yeah, AtomP worked fairly well as well with the increased augmentation and regularization. So I'm going to go back up and look for a table, which, yeah. So yeah, here's, we compared the output of our models on ImageNet v2. I believe that was the matched frequency variant of that data set, just mostly for a sanity check to make sure we weren't overfitting while we were searching for the hyperparameters. And it's interesting to see that like the best ImageNet 1K weights are definitely not necessarily the best V2 weights. I've done some other measurements myself on other out of distribution or alternate test sets like ImageNet adversarial, ImageNet rendition, ImageNet sketch, and it's pretty much the same. You see quite a scattershot graph like that when you're comparing best accuracies on the train val don't necessarily line up with the best transfer to other data sets, but there's definitely correlations there. So overall, if you use similar ingredients like high augmentation regularization, you will end up with generally better results on the out of distribution test set, especially the challenging ones like rendition and adversarial. So I think I've covered the basics of the paper. I'm going to switch my screen now. So this is actually some analysis I was doing for NeurIPS workshop purposes, but I think it's relevant here. This is looking at the broader timm as a whole. So basically all of the models in timm that have pre-trained weights are in these graphs. And these are basically, if you see architectural papers these days, you'll often see the Pareto curve with a plot of top one accuracy versus parameter counts, flops, which are usually Gmax, or some sort of inference or training latency. As some people have seen on Twitter, I mentioned don't use param counts, and there's some other researchers that share that view. Although these graphs are highly dependent on what kind of hardware you're using, and GPUs particularly line up well with activation counts, which relates to their bottlenecks, usually often memory bandwidth. But if you just even look at top one versus latency on the hardware, can see quite a spread across all the architectures. So this one is split out into CNNs, roughly ConvNets, vision transformers, and the mixer MLP type networks. I'm going to go to the next graph, which is a little bit of a color explosion. So this one I tried to trace out all of the pre-training sources for the models in timm. And you can see the type of data and the techniques that you're training with have a pretty outsized impact on the vertical spread of a given model architecture. The ResNet 50s are all roughly in this band here. And it's interesting that they span a pretty big chunk of the the vertical space from 75, 76-ish of the Torch Vision like originals up into the recently trained, that's the V250, but similar hyperparameters to the V1s in the ResNet Strikes Back paper. They have a pretty widespread, and that's all based on augmentation and regularization. And then in terms of larger data sets, you can see like the 21K BIT models, and these yellow dots are the noisy student efficient nets that had access to some JFT 300M pre-training. They stand out at the top of the curve. But yeah, it's interesting when you put everything in context, is like it's a pretty noisy jumble, and I hope that illustrates that it can be really challenging to compare one model architecture to another, or basically any data points, data sets, augmentations, regularization, without thorough analysis and lots of comparisons, because there's quite a bit of variation there. I should also, the Levitt models are actually really interesting. They stand alone on this curve in terms of latency for performance. And I think some people pointed out that this is an interesting architecture, but not a lot of people actually know about it.
Thank you very much.